Hello, everybody. I'm super excited that all of you could come to this CodeLabs Tech Talk, which also happens to be our last CodeLabs Tech Talk. I'm super excited that all of you could come to all of these events throughout the program. Today, we're going to be hearing from Vivek, who is a software engineer at Walmart Labs, and Aditi, who is an ML engineer at Microsoft. Today, they will be talking about the continuous integration and delivery of machine learning models.
Thanks, Cora, for introducing us. Hi, everyone. I'm Aditi. So let's begin the talk with a brief history of CI/CD. So a long time ago, in the pre-agile era, software teams worked on projects and features for months with a predetermined day in mind for integration and deployment. So this process led to some major problems. Integrating months of work by multiple teams led to a large number of merge conflicts. Features developed by different teams over a period of time were sometimes incompatible with each other, and this fact remained unknown until the very end. And since all the changes were integrated together, it became difficult to roll back if one of the features did not work at all. So that's when CI/CD came to the rescue. So CI, or continuous integration, is basically a software development practice where members of a team integrate their work frequently, and each integration is verified by an automated build to detect integration errors as early as possible. So this approach basically leads to less integration problems and allows a team to develop their software rapidly. CD, or continuous delivery, is the ability to get all the changes, like all the bug fixes, configuration changes, and all the new features into production as early as possible and in a sustainable way. So let's try and understand how our ML applications different from traditional software applications. So as most of you might know, a traditional software application workflow looks something like this. You edit your code, you push it to the repository, there's an automatic build trigger, which runs some unit tests and integration tests in the background. And if everything is good to go, there's an artifact created, and that artifact is continuously deployed into the production with a continuous deployment pipeline. So the process for deploying and monitoring ML application is much more complex because an ML application is subject to change in three axes: the code, the model, and the data. So this is a very famous picture from a research paper by Google called Hidden Technical Depth in Machine Learning Systems. I suggest you all give it a read. So this basically talks about the ML code is a very tiny bit in the whole ML system. And there are various components associated with productionizing a ML application. So some of the major challenges in an ML application include team skills. So in an ML project, the team usually includes data scientists or ML researchers who basically focus on EDA, model development, and experimentations. So these members might not be as experienced as software engineers in building production class services. The second challenge is development. So ML application is experimental in nature. You try out different features, algorithms, modeling techniques, and it's very difficult to keep a track of what worked and what did not. The third challenge comes in testing. So ML systems are more involved than just unit and integration tests because you need to have tests for data validation, train model quality evaluation, and model validation. The fourth challenge is deployment. ML systems are not about just deploying offline trained ML models into prediction as a prediction service, but ML systems require continuous training and deployment as the data keeps evolving in our streaming platform. The last challenge is productionizing ML systems. So ML systems continuously have reduced performance, not just because of suboptimal coding, but also due to constantly evolving data profiles. So keeping in mind all these challenges, it's the need of the hour to evolve our ML CI/CD pipeline. So for this workshop, we have created a sample ML CI/CD pipeline, and my friend Vivek is going to be walking you through the pipeline. So just a disclaimer, the pipeline is not an exact production grade pipeline that runs at Microsoft, Amazon, or Walmart, but this captures the essence of how a typical ML application automated workflow would look like. So over to you, Vivek.
Hi everyone, thanks Aditi. So as you guys can see on my screen, I have a sample CI/CD workflow. Now this might look a bit complicated at first, but we'll break it down to each component. So the starting point of the workflow, you can see that we have a data warehouse and we have an external data source from which the data is coming in. Right in between of this external data source and this data warehouse sits an ingestion module. Let's discuss what everything is. The external data source can be anything from where your data is coming in. It can be your own live application from which you are having a feedback loop, which is ingesting data in your system. This can also be some external Spark streaming, some messaging queue, or even flat CSV files. Anything works as long as you are getting the required data into your data warehouse. This ingestion module is responsible for validating this data. As you all know, even if you have one bad record in your data warehouse, it can break your whole pipeline. Your training will fail, your model evaluation will fail, everything will fail. So this ingestion module is responsible for filtering out those bad records, making any transformation on the data if you need to, and then ingesting it into your data warehouse. Okay, once we have the data, what do we do next? So as you can see down here, there are usually two types of programmers who work on machine learning applications. The first category is software engineers and then data scientists. Now these both programmers work in parallel workflows and their work is merged together down somewhere in the pipeline, which then gets served to users. So let's discuss each of them one by one. Let's start with software engineers. So we have a software engineer. She's using her favorite IDE, which happened to be Visual Studio Code in this case, make some changes and commits into the source code repository. Now I should say that software engineers are not responsible for building the models. They are just creating the infrastructure that is surrounding the model, like the web interface through which we expose an HTTP endpoint to end users or any consumers who would be interested in taking advantage of our model. Okay, so once the code is in the source code repository, a CI server or a CI/CD server, which in our case is Azure DevOps, will notice. So it is constantly looking at this repository for changes. As soon as there is a change, it will note that, okay, some new code has come in. What should I do? An automatic build will be triggered. Now the builds can be of two types. One is called a PR build or a pull request build. Another one is called a master branch build. How are those two different? So let's think of it this way. On the primary branch or the master branch, you have your code which is running in production. It is well tested, it is well validated. Now you don't want unchanged or untested code getting merged into your master branch. So developers or software engineers create a different branch, make their changes over there, develop any new feature that they want to on that new branch, and then push that new branch to the source code repository. Okay, this CI/CD server sees that a new branch has come in, and since it's a new branch, it's not your primary branch, it will automatically trigger a pull request build. The pull request build will test your code and do any kind of validation that you may have set in. Now, those validation could be linting errors. Those validation could mean running your integration test, your unit test, or any other kind of test that you may have configured in your CI server. If those evaluation and those tests pass, the CI/CD server will send a flag to your repository saying, okay, this pull request seems good. All the tests are passing, all the validations are passing. Everything is good. Now, the maintainer of the source code repository will look at the pull request. We'll see, okay, all the automated tests are successful. We'll review the code manually if that person needs to, and then merge the code into the master branch. Once the code has been merged into the master branch, a new build will be triggered. That build is called the master branch build. Okay. Now the master branch build does everything that a pull request build does. That is testing the code, running unit test cases, validating for linting errors or any other tests that you may have configured. But in addition to that, it will also build a deployment package. Now, the deployment package can be anything. It could be jar files for Java application. It could be an NPM package, a Python package. In our case, it's a Docker image. Now, the reason for using Docker image is because it has become an industry standard these days, and it's very convenient to deploy. So we are, in our example, using a Docker image. This Azure pipeline or this DevOps server is responsible for building the Docker image and then pushing the new image to container registry. Now, if you don't know what a container registry is, think of it as a place where you can store all your Docker images. You can also think of it as GitHub for Docker images. Just like in GitHub, you store all your Git repositories. In container registry, you store all your Docker images. A container registry has also some other features, like you can version your Docker images, have multiple versions stored together, and you can just request any version that you want to. Once the code, the Docker image is in the container registry, a trigger will be executed. That trigger will push the Docker image to the server, which is running our code in production. So the new Docker image will come from here, this path, into the backend service. And once the Docker image is started and a new Docker container is running, our latest code that was changed by the software engineer will start running in the backend service. Okay. Now that we know how our software engineering workflow looks like, let's look at the data scientist workflow. Excuse me, I need to sip some water. Okay, so data scientists. Data scientists are responsible for exploring the data, making any transformations in the data they want, doing feature engineering, building model, and evaluating those models before they push into the production. Now, data scientists, using their favorite IDE, which happens to be Jupyter Notebook in this case, and usually this is the choice of IDE for most of the data scientists. They pull data from the data warehouse, do exploratory data analysis, run experiments, tune hyperparameters, or make any kind of changes they want, build several models, test them out, and see which one works best for their application. So let's say that after multiple iterations, data scientist has come to a very good model that she thinks that is good for production. Now that model will have some configuration parameters. Configuration parameters can include, if it's a neural network, how many layers do I need? How many neurons should be in each layer? What should be the hyperparameters? For example, what should be the dropout probability? What should be the L2 regularization coefficient? Things like that. Once those things are decided, the data scientist would push all those configuration changes into configuration repository. This configuration repository can be something as simple as a YAML file, JSON file, or even a property files, which in our case is also a YAML file, and it's sitting in an Azure blob storage container. Okay. Once the configuration has been pushed into the configuration repository, data scientist will trigger this job called train, evaluate, deploy. Now, you all know that machine learning training is very compute extensive. The server that is training the machine learning model should not be running all the time. So this job will be responsible for initializing all the servers, the resources, or the cloud virtual machines, anything that you are using, and then sending this experiment code over to that server, and then starting model training. Once the model has been trained, there is a script which automatically checks or automatically evaluates the model. The evaluation could be as simple as checking if the accuracy of the model passes a certain threshold. Let's say I want that my model should have at least 0.85 or 85% of accuracy before I will push it into production. That's my benchmark. If a model during this training achieves an accuracy lower than that threshold, I will not do anything with that model. I'll just discard that model, send a notification to the data scientist, okay, your model training failed, something is bad, look into it. But if the evaluation is successful, that new model will be sent to this model repository. Now this model repository can also be very simple. In our case, it's just an Azure blob storage container, which is containing all the binary model files that we have exported into that container. This job is not replacing the existing model from the model repository. Rather, it is creating a new version of the model and then pushing that new version into this repository. Okay. Right here, we see something called model serving. Okay, what is that? Now, deploying machine learning application usually comes with like two strategies. There are two strategies which people usually follow in industry to deploy machine learning models. One is called the embedded model. Another one is called model serving. Now in the embedded model, you'd have that model file included in that backend service package. You'll have your API, which could be PyTorch, TensorFlow, scikit-learn. You'll use those APIs to make predictions. The backend code further down in the execution flow will read that outcome from that model prediction and expose it as a service using HTTP to the end users. Now, this has one problem, that software engineers who may not know things about machine learning or data science will have to use machine learning models and have to know their APIs. Now, to tackle those issues, people generally use this model serving strategy. Model serving is a dedicated service which is responsible only for making machine learning predictions and nothing else. Okay, so this will have the model, it will have an API, it could be a REST API using JSON, it could be a gRPC, you can send protobuf, anything that you want. And this, it will take in a request and it will give a response, which will be prediction from the model. Okay. Just as I mentioned, the advantage of having a model serving is that it completely abstracts out the machine learning component from the software component. And because of this, if anybody, a software engineer, is not familiar with machine learning concepts, they can think of this model serving as just another REST API on which they can send a request and get a response and everything is good. Right here, you can also see something called logs and monitoring. Now, we all know that machine learning systems or machine learning models decay much faster than traditional software. Why? Because data is continuously changing. You know, let's say you have a model for predicting revenue from ads on an online website, like on a retail. Let's say I work for Walmart. So on walmart.com, we show ads. And we have a model which is predicting revenue of every day on our advertising platform. Now, during normal hours, I take in consideration what was the revenue, and my model takes into consideration what was my revenue in the last 30 days. And based on that 30 days, it predicts what will be my revenue on next 2 or 3 days. Okay, but that can fail. Let's say it's Thanksgiving, and the sales on Thanksgiving, as we all know, it's like much higher than on regular days. So my model will definitely fail. Because of those constraints, my model needs to continuously evolve, right? So for evolving the model, we use something called continuous training. Okay, what is continuous training? So we check for new incoming data, we monitor the changes in real world, and as things change, these data scientists were responsible for continuously building new models, pushing those models into model repository, and then serving from those new models. Okay. There's also one thing. So this model serving here, this is configured in such a way that it's constantly looking for new models into this model repository. Okay. So once a new version of the model has been pushed here, after a set amount of time, however you configure it, this model serving will know that a new version of model has come into the model repository. Once it finds it, it will pull the new model into model serving, load it into memory, and start making predictions using the new model. Okay? So as you can see, I did not say that I have to deploy the model manually or do any kind of thing. The model serving is responsible for pulling the new model automatically. Okay? You can think of this as continuous deployment of model. A new model comes in, model serving pull it, and start making predictions from this model. Okay. Now, I have a sample applications which has incorporated this very simple workflow. So I'll go over it and we will just see how the simple pipeline can be incorporated. Okay, let's get started. So the application that we are building, let me open it. So the application that we are building makes prediction whether an applicant would get an admission at university based on certain parameters. Those parameters can be the GRE score, the TOEFL score, university rating, and other kinds of parameters. Okay, so this is my backend service, and if I make a request to my backend service, I see that based on these parameters, the applicant will get an admission. There's something called model version here, which like after some time you'll see why is important. And we have a confidence score. So my model is 73% confident that the applicant will get an admission. Let's change some parameters and see if something changes. So let's say the person has very bad TOEFL score, very bad GRE score. We send, the model this time is 99% confidence that the applicant will not get an admission into the university. Okay. If I go to the workflow, we have a data warehouse. Let's look into our data warehouse and see what's in there. So this is our table. So the data warehouse can be very complex, but it can be very simple. We can have NoSQL databases, Hadoop or Spark clusters. In our case, we're just using a Azure SQL relational database, and it's just one table. So this table has multiple records. Each entry represents one applicant, and these columns represent their parameters. The last one is the label, whether the applicant got admission or they did not get admission. Okay. The next component is this external data sources and ingestion module. So I mentioned this ingestion module is responsible for filtering out bad data. Let's run a sample script and see how does that work. So here in my IDE, clear that. I have this data ingestion module. I have this script which does this data validation or data testing. It checks whether the score is between a certain range, whether the research value is good or not. And if these validations fail, it will not ingest the data. Let's run something and see how that looks like. So I get a message that all inputs have been processed. So I should show you that I have a flat CSV file which has 14 entries. Some of the entries are bad, some of the entries are good. The script is reading from that CSV file and ingesting into our databases. So it says ingested one row, and here it says there's a warning. Okay, so some kind of validation failed. It says that the GPA should be between 5 and 0. Okay, but the GPA was not in that range. GPA was more than that. So there was validation error, but the ingestion pipeline did not stop. It completely ignored that record and moved on ingesting the new records. Okay. The next thing we discussed about is software engineering making changes and that change getting deployed into our backend service through this Azure DevOps pipeline. Okay, let's do that and see what happens. Okay, so I have my source code here. Let's make some small change and see if my build will be triggered. So before that happens, I can show that this is my dashboard where I have my job configured, the CI/CD job. Okay, so let's say this is my README file. I'm just making a dummy change, nothing which is actually changing anything, just for demonstration. So I just made a space here. I will do git add README and do git commit, do dummy change for demo. I have my commit locally. I'll do a git push. Okay, something has happened. Okay, somebody has changed that, so I need to do a git pull first. Oh, this is bad. I have some conflicts. Give me just 1 minute and I can totally resolve everything. Okay, so everything is resolved. Git again. Conflicts. And then do a git push. Okay, so my changes have been pushed. Let's go to our repository and look at our source code. How do I? Okay. So this is my repository. I see kind of an orange badge here. That means my build had started 35 seconds ago. If I go to my Azure pipeline, I can see that a new build has been triggered. Okay. And this build is running. If I go inside of the build, I can see it is currently testing. Once testing is complete, it will do this build and deploy. Let's go inside and look at the logs of what it is doing. Okay. Now, while this is running, why don't we go into looking at how do we configure this kind of thing? So if I go into my repository, I can see there's a file called Azure pipelines.yml. Okay. Now this file will change depending on what kind of CI service you're using. If you're using the Travis CI build, this file will be .travis.yml. If you're Jenkins, it would be something different. To go very briefly of what it does, you can see it has stages. The stages that we see here, test and build. So it has a test job, it has the build and deploy job. The test job is using Python 3.6. It is installing all the dependencies for the Python application. It is running the unit test that we have written using PyTest. If it succeeds, it moves on to the build and deploy stage. This build and deploy stage is building our Docker images, and then it is logging into the Docker container registry that we just saw, and then it pushes those Docker images to the Docker registry. Okay. If you feel that you are overwhelmed, how you don't understand the syntax or how do you configure those things, we will be adding the steps of how to configure these things into Azure into our README later after this talk. So feel free to check those. Let's check the status of our build. So as you can see that it was doing testing here, and it says that the testing has passed. Okay, so that's a good news. So right now our job is like very simple. That's why this build is taking only like 2 or 3 minutes or maybe 5 minutes. But in real world, you can expect your builds to run for even hours. There will be thousands or even like tens of thousands of tests which will run, and they will interact with like other services and things like that. So build, it's totally normal if the build is running for a very long time. So the test has passed. It is currently building our Docker image. And I think the Docker image build is successful. It is logged into the Docker image. It is pushing new image into our container registry. Let's wait for this to complete. It looks like it has completed. Okay, so let's move to Azure and see if our image has been pushed. Okay, so I'm on Azure container registry, and like we saw in this R diagram here, that there'd be two kind of services. One is model serving and backend service. So this is building both of those Docker images here. So we have model serving, we have backend service. Like look into one of it, and we can see that it has been, let's refresh it, and we can see that it has been updated right now. So I'm in Pacific time, so it's 10 a.m. right now. It has been updated recently, and it has been updated from our CI build. Okay. I also mentioned that once a new image has been pushed, it will automatically trigger deployment of that image. Okay, so that can be configured using something called a webhooks into Azure. So here, those are the webhooks, and this webhook for backend service is deploying. So you can see all the deployments that we have done in the last 2 days while we are building the demo. And so this will deploy your Docker image into this backend service app that we have created in Azure. The backend service app also is a feature of Microsoft Azure, which is like a very easy way of deploying Docker images. It doesn't have something fancy like Kubernetes cluster or auto scaling or things like that, but it does the basics. Okay, so this is the app. This is the dashboard where you can monitor your logs and do stuff like that. Okay. Now we are done with our software engineering workflow. Let's look at the data scientist workflow in action. I mentioned that this version, model version, is important, right? Now we'll see why. So we are storing our model into a model repository, right? So you can see that we have built 6 versions of our model, version 1 to version 6. I'll start a training, and if the training is successful, it will create a new version and push it to this model repository. Let's do that. I'll go into my IDE. I will go to this train, eval, and deploy job. Okay. We don't have to pass any configuration parameters because I mentioned that the configuration is already set into the configuration repository. I should also go back there and show you how that configuration looks like. So this is a basic YAML configuration. So for model training, I'm setting a hyperparameter that I should have at least 1,000 iterations during my gradient descent. And I'm also setting that the evaluation threshold, which is 85% in this case. So my model should at least have 85% accuracy before the new version is pushed into the model repository. Okay, let's go to the IDE and run this train and deploy job. Okay, so you can see in the logs that it has loaded the latest application configuration from the model repository. It does not have any configuration. We see that the model has been trained with 93% accuracy, which is really good. It has created a new version of the model, model version 7, and it has successfully uploaded the model into our model repository. If we go to the model repository, let's close this. I can see that there's version 7 of the model, okay? I also mentioned that the model serving is constantly looking for new models in the model repository, okay? So if that listener has triggered and the new model has loaded, my new latest version of model should be used in my backend service, right? So right now I have configured it 30 seconds. Every 30 seconds it's listening for the model. That's just for demonstration. In real world, you should have something like 1 hour or even a day. But it's a demo we don't have all day, so it's just 30 seconds. Let's go into our REST client and see if the new version has been loaded. Let's make a request. So you can see that this new version of the model is being now used, version 7. So you can see that we don't have to do any manual deployment. I just triggered a script. That new script deployed the model. The model serving, using its listener, loaded the new model and started using it, okay? Now, what if you want to use some older version of the model? You don't want to use the latest version, right? You deployed, everything was good in evaluation phase, but something bad happened in production. Things like that happen, right? You want to go back to previous version of model. Okay? So the model serving, it's smart. It doesn't have only the latest version of the model. It has all the previous versions as well, or however many versions you have configured it to have, okay? In this case, we are not eliminating any previous version of the model, so it has everything, okay? So while making a request to our model serving, we can specify the model version we want to use. So in here, I have my model serving REST endpoint, and this is just giving me the latest version. So let's hit it and see, okay, version 7 is the latest. Let's make a prediction using the latest version in model serving. Just to mention, the endpoints are different. This one was the backend service, and this one was the model serving. Right now, they're giving the same response, but in real world, where you have user interfaces or things like that, the response will be HTML instead of JSON. Okay, so my model serving endpoint, I have this predict URL, and I make a request. I get version 7. I don't want to use version 7. I want to use something else. So I can specify that. Here, let's say I want to use version 5, and I make the request. Okay, so you can see that this model, this endpoint has used version 5 to serve the request. Okay, so it just gives you the flexibility of using any version of the model that you want to. Okay, in like industries where they run experiments in production all the time, this is very helpful. Now, in our pipeline, where is our pipeline? Yeah, in our pipeline, we don't see something called A/B testing module here, right? But ideally, there should be something called A/B testing module that you'd run both those models, like version 6 and version 5 parallelly, and those will be used by different control groups. And you will capture metrics from both of those models and see that which one is doing better in production, okay? And after like a certain amount of set time during which your experiment is running, you'll decide that, okay, this model is good, I should use that one in production, right? Okay, one thing that I did not discuss about this picture is this red dot and this service, data monitoring. Okay, what is that? During our experiments, this data scientist is manually triggering train, eval, deploy. Right? This process is manual. It doesn't have to be that way. Okay, if you're confident that configuration parameters is good, you don't need any kind of manual intervention to constantly improve your model, you can have something like this. Now this data monitoring service is constantly looking at this data warehouse. It is looking for new data, okay? Let's say I am set it that if 500 new records come in, I want to retrain my model because my data has evolved beyond a certain threshold, okay? It checks the data warehouse periodically. It sees, okay, something has changed, new data has come in. It will trigger this train eval deploy job, and this train eval deploy job will do as it does. It will build the module, evaluate it, and push it to this module repository, okay? And the model server will listen to it and do this. So in our demo application, we don't have this. So I would encourage you to implement this kind of feature into your model, try ingesting data into data warehouse and see if you're automatically training the model job is triggered or not. Okay, so I think that's about it from us. Feel free to ask any questions that you have. We're waiting for your questions.
Awesome. Well, we already have 2 questions right now, and I invite any attendees who have additional questions to just pop them in the Q&A box. We have one question from an attendee asking, what sort of sanity checks would you put in place as a data science throughout this process? For example, you couldn't just have validation accuracy above X number because your model could be overfitting.
Yeah, that's a very good question. Aditi, would you like to answer that?
Yeah, sure. So some of the checks that we can take into account apart from accuracy is checking for other different metrics. For example, if you have a classification problem, what you can look for is precision, recall, F1 score, and all other kinds of metrics that a classification problems takes into account. For a regression problem, you can look at different values like R squared, RMSE, and other metrics that fit into a regression problem. And one thing that you can also look for is, like Vivek mentioned, like having 2 versions of your model into production so that you can check how those models are actually performing in production, because the training data could be different from what you actually observe in production. So having 2 models that you can compare, like a A/B test, using a A/B test is a great way to validate how your models are performing in production. Other than that, you can have different metrics apart from just accuracy, like an F1 score or precision recall or RMSE or R square, depending upon the kind of problem you're solving.
Awesome, thank you for that answer. We have another question that's asking, what steps would you take if you had a large problem with your data and or model? For example, if you found out your recommendation system is in a feedback loop, that's typically not a problem that happens overnight.
So for those kind of problems, what we do is we put the model into production, and we are also we have logs and monitoring in place to check the performance of our recommendation engine. And that's when online training comes into place. So you put a model into production, you give the recommendations according to the model, and you're continuously checking for the performance of the model as well using the logs. So once you have like the performance of the model, you can change the hyperparameters of the model and retrain it again. That can be done either through an automated pipeline or manually. It's mostly manual because you need to work with different hyperparameters. So that's kind of a manual process. But yeah, you do put your model into production, and then you're continuously improving it using your logs.
Awesome, thank you for that answer. We have another question from an attendee saying that the talk was great, and how do you keep the data version which was attached to the particular model version? The feature engineering might have been different. That's
yes. So if you are making such amazing, so our CI/CD pipeline right now does not account for changing the data version. So if like my data had initially only 8 fields, right now I'm getting 10 fields. So I have to change my model, right? So in that case, you will have a completely different model, because in the prediction pipeline, you have to tell the software engineers as well, okay, you cannot just pass in the 8 parameters, you have to pass in 12 parameters right now. Okay, so this is something called so if like in an industry, if you have like multiple servers, we will build the new model and deploy those new model into a different set of servers, okay? And we'll route traffic depending on which person is requesting, okay? Once we are confident that this new model on this new set of servers is running fine, then we will slowly decommission those old servers, remove old deployments from the previous servers, and only have the new servers running in. So you will typically think of this as a migration job, okay? So you're migrating your model to a completely new version. So think of it like a major version change. Okay, these model version change that I saw, it was kind of a minor version change. You don't have to change anything, everything works automatically. But that would be a major version change where you need some kind of model manual intervention because a lot of things have to be changing. But the good thing with this pipeline is that you can just run a parallel pipeline and deploy that to a different set of servers instead of the current set of servers, divert traffic to those servers, test it for some time, and then decommission the old ones. Traditionally, you would call that as a blue-green deployment system. Okay, I think that answers your question.
Awesome. Well, we have another question about an attendee who may have missed part of the discussion, inquiring about the use of cloud servers versus running it on your own machine and the differences and about that.
Okay, use of cloud servers versus, so I mean, traditionally everybody used to have their own data centers and they had their own machines in-house. Now the problem with that, so I work for Walmart and I'll tell you what happened at Walmart, okay? So everybody knows that during holidays, there's way too much shopping than on normal days, okay? So if I have my in-house data center, I'm actually buying the servers, right? And I'm seeing that Thanksgiving is coming. I bought a bunch of servers. I spent millions of dollars on those servers. Once Thanksgiving is over, I don't need to run at that capacity. Okay, so all those servers are sitting, okay, in my data warehouse and dust is settling on them. I don't want that. It's a waste of money. So Walmart is currently moving to Azure. Okay. So what you do in cloud services, you don't buy the servers, you rent them. Okay. And you can rent for the shortest amount of period possible. Okay. So I'm running only on 10 servers on my regular time. So right now I'm running on 10 servers. On Thanksgiving, I expect 5x load. So I rented 40 more. I have 50 servers. I ran those for 1 month. And then I said, okay, I'm done with it. I give the servers back to Azure and I'm saving money. So basically running on cloud is all about saving money. Initially, the concept started at Amazon, like they bought a lot of servers during holidays. And somebody at Amazon said, okay, we have bought all the servers. What should we do with it? Okay, we are wasting it. So some guy came up and said, why don't we rent these? And that's how the concept of cloud computing came along. Now, as cloud computing has evolved, they have started to include a lot of features into their interfaces. So you can think of it as platform as a service. You don't have to buy hardware, manually install your operating system, your drivers, and things like that. You can just click some buttons and you can create your server. You can create a database with some workflow, some 5 or 10 clicks on your button, configure your network and things like that. So cloud has made things incredibly easy, even if you're not a network or a system expert, right? So the primary goal of cloud was to reduce cost, but as things have evolved, cloud has become much more easier than having your own data center.
Awesome. Thank you for that answer. And I think just to further answer this attendee's question, the attendee asked where this model was running, and this model is running on the cloud, correct?
Yes, this model is running on cloud. It's running on Azure.
And for students who want to just get started with running machine learning models, do you recommend that they work on their own computer or start learning about working on the cloud?
So I would say that while you are building a model, running experiments, do everything locally. Like even in this demo, this training, evaluate, everything is happening locally. But once you have everything in set, you want the world to use your model. You just don't want your model sitting on your computer, right? You have to deploy it. And while that phase comes along, you should use a cloud service. Okay, I think all the cloud service, GCP, Azure, or AWS, anything that you want to use, they all have a free trial, and you can like spin up services which are like minimal. They are not production grade, but they're good for testing and education, and they can deploy to those and test it out. And this DevOps like Azure CI/CD or even Travis CI/CD, any CI/CD pipeline, there are tons of free services which provide free CI/CD. You can use any of those. Also, if you want to know how we have configured everything, so like I mentioned, we'll be adding the steps and the links in the README. So feel free to check those after the talk, and this will surely be updated very soon.
So specifically for Azure, every person who registers on Azure gets $100 of free credit, and I think that's a lot of money to just try out if you want to just learn how the infrastructure works. So even I'm using my free credits for this project, so I think all of the students can go and try on Azure itself.
Awesome. And will you send the link to the GitHub repository to me after the talk so I can share it with the students?
Yeah, absolutely.
Awesome. And now we have another question, and I invite any attendees who have any last questions to ask them now. Do you have any advice for new grads hoping to break into machine learning?
Yeah, so there is a lot of advice online right now, and it's difficult to navigate in the scenario. But personally, like given my career, I would suggest people to try out small projects, like just pick up a problem they like if they're interested in natural language processing, or if they're interested in speech, or just like basic machine learning. I would suggest them to try out like an end-to-end machine learning pipeline thing, and not just like training models locally on a Jupyter notebook, because that's not how industry works. So my personal suggestion would be to see how they're processing data and how they're training their models, and then how would they productionize their model. So these steps include like these. Basically, you need to focus on modularizing your code properly so that you can reuse different components of your part. For example, if you've worked with feature extraction already, and you want to just keep on trying different models, like try logistic regression, random forest, or any other gradient boosting model. So you should be able to reuse the same feature extraction pipeline for different model experiments. So it's basically pick up a problem and try it end to end, and try to show those projects on GitHub. And when you're showing your projects to the world, you ensure that your code is clean and it has a good README file. You document all your steps well. So basically, coming up with a project in an end-to-end way is the best way to go about learning machine learning right now.
Awesome. Thank you for that answer. And in regards to an attendee who asked about a recording, the recording will be posted for attendees to look at afterwards. I posted the link in the Q&A box of where specifically it'll be. So we have one final question asking, what would be a good data set to practice CI/CD with new influxes of data? Typically, Kaggle or academic data sets don't have that.
So while we were researching for this project, we came along a very good data set on Kaggle, which is like predicting daily Bitcoin prices, which is like a streaming data. So you can build into your pipeline like the CT part of it, continuous training part of it, and other components remain the same as we discussed. But like a Bitcoin data set would be like predicting the daily prices of Bitcoin. That's a data set publicly available, and it's a good start to try out different components that we just talked about in the CI/CD pipeline.
Awesome. Thank you so much. Well, it looks like those are all the questions that we have today. I want to thank both of you for this amazing talk and all the amazing preparation you did. I'm sure students really appreciate it. And I want to wish everybody a happy rest of their day.
Yeah. Okay. Thanks a lot.
Thanks so much.
Goodbye, everybody.
Bye-bye.